Okay, let's just try and unpack this. The sheer scale of the universe.
Yeah.
It really hits you, doesn't it?
It absolutely does. The numbers are just staggering.
Yeah, like consider this. Our closest galactic neighbor, Andromeda, it's 2.5 million light years away.
Which sounds like a lot, and, well, it is a lot.
Right. To really get it, if we could somehow jump in a spacecraft, go at, say, 28,000 kilometers an hour, pretty fast.
Seems fast for us, yeah.
It would still take us, get this, 94.5 billion years to get to Andromeda. Billion.
Just completely impractical with current or even foreseeable tech.
Exactly. And even if we hit the absolute speed limit, light speed, still 2.5 million years.
So yeah, the universe is big.
Yeah.
Really big. It puts a fundamental barrier on just popping over to the next galaxy.
Which naturally leads to the big question. Is there, a shortcut? Some cosmic cheat code?
A way around the speed limit, essentially.
That's where wormholes come in. I think for a lot of us, the first time we saw that was maybe in a movie, right?
Yeah.
Interstellar.
Interstellar definitely popularized the visual of that trip through the wormhole near Saturn.
Yeah. They just zip through and bam, another galaxy. Almost instant.
And it's interesting, they did consult with physicists, Kip Thorne notably, to make it look, well, scientifically plausible, at least based on the theories.
And that's the really cool part, isn't it? This isn't just like total fantasy writing.
Not entirely, no.
The idea, the concept of wormholes, it actually comes from real science. From Einstein's theory of relativity, believe it or not.
That's right. It's deeply rooted in the mathematics of general relativity.
So that's our mission for this deep dive. We want to unpack the science, look at the theory behind wormholes.
The possibilities and, let's be honest, the huge challenges.
Absolutely. And we'll touch on black holes and white holes too, because they're sort of related concepts that pop out of the same science.
Exactly. To really get wormholes, you have to start with the foundation. Einstein's general theory of relativity from 1915.
The field equations, which are famously complex, right?
Oh, incredibly complex. 10 nonlinear partial differential equations, essentially. But the core idea, revolutionary.
It's that matter and energy actually warp space and time.
Precisely. They dictate the geometry, the curvature of space-time itself.
Like that analogy of a heavy ball on a rubber sheet. It creates a dip, a curve.
That's a great way to visualize it. Planets, stars.
Yeah.
They bend the space-time fabric around them. More mass, more gravity means a deeper curve.
And Einstein himself, he only found approximate answers to his own equations.
In specific cases, yes. It was actually Carl Schwarzschild, just a year later in 1916, who found the first exact solution.
And that led to?
That solution describes something truly bizarre. A singularity, a point of infinite density surrounded by an event horizon. It predicted black holes.
Wow. So the math predicted black holes decades before we had any proof, let alone that photo in 2019.
Decades, yeah. It's a testament to the power of the theory. That first image was a stunning confirmation of what the equations told us was possible.
Okay, so black holes are one mind-bending result. But you said wormholes are another solution to those same equations. How does that work?
Well, think of a simpler math problem, like a quadratic equation. Sometimes you get two perfectly valid answers, right?
Like x squared equals 4 gives you x or 2 or x equals 2.
Exactly. Einstein's equations are vastly more complicated, so they can also allow for multiple different theoretically valid descriptions of reality.
And one of those is a wormhole.
One of those, yes. Proposed by Einstein himself and his assistant Nathan Rosen back in 1935, it's formally called the Einstein-Rosen bridge.
Einstein-Rosen bridge. Okay, so how do we picture this bridge? It's not like the Golden Gate, I assume.
No, not quite. The standard analogy uses a piece of paper. Imagine it's flat, 2D space.
Okay.
You've got point A on one side, point B on the other. The shortest path is a straight line across the paper.
Right.
But what if you bend the paper, fold it over through the third dimension so A and B are almost touching?
Then you could just poke straight through the paper, a much shorter path.
Precisely. A wormhole, theoretically, does something similar. It bends our 3D space through a hypothetical fourth spatial dimension.
Creating a shortcut.
Yep.
A tunnel connecting two distant points in space, or maybe even time.
Exactly. It's like your travel example flying from Delhi to New York.
Yeah, on a flat map, it looks like a long curve, maybe going across Europe.
But the shortest actual path in 3D goes over the Arctic, closer to the North Pole. It looks longer on the 2D map, but it's shorter on the 3D globe.
Because the Earth is curved. So the wormhole is like a curve in space itself.
A curve, or maybe more like a tunnel. The name wormhole actually came later from John Wheeler in 1957.
Yeah. Okay.
He used the analogy of a worm on an apple. Instead of crawling all the way around the surface.
He just burrows straight through the apple. A shortcut.
That's the idea. Extreme gravity warping space-time so much it forms a connection, a tunnel.
So those pictures we see, the sort of funnel shapes meeting in the middle, this is a 2D simplification.
It's a helpful visualization, yes. But if they exist, they'd likely be spherical. Entering one wouldn't look like entering a tunnel entrance.
Spherical. How would that look?
Imagine approaching a sphere. As you get closer, the view of the universe through the sphere would be distorted, showing you the space on the other side, but warped. Like looking through a fisheye lens, maybe? Interstellar actually did a pretty good job visualizing that spherical, distorted view.
Wild. Okay, but if you can take a shortcut like that, potentially faster than light could travel the long way.
Yeah.
Does that mean time travel?
That's one of the most startling implications, yes. If you could traverse the wormhole effectively instantaneously.
You'd arrive somewhere before light from your starting point gets there.
Potentially, yes. Depending on the wormhole's properties and how it connects points in space-time, it could theoretically allow for jumps forward or backward in time.
Whoa. Okay, mind officially blown. But let's pull back a bit. The challenges. How do you even make one? What creates that kind of space-bending gravity?
That's a huge question. The gravity needed would be immense, truly astronomical, which leads back to black holes.
So maybe black holes are involved in forming them.
That was the initial idea from Einstein and Rosen, yes.
Yeah.
Perhaps a black hole could be one mouth of the wormhole?
Right, the ultimate gravitational source.
Mm-hmm.
But if you go into a black hole, you don't come out. So if a black hole is the entrance...
What's the exit? That's the problem. If the other end is also a black hole, well, you're trapped. It's not much of a shortcut.
Doesn't help you get to Andromeda then, just stuck in a different black hole.
Exactly. Which brings us to the theoretical counterpart. White holes?
White holes.
Yeah.
Okay, the name implies the opposite.
Precisely. They're another theoretical possibility from Einstein's equations. If nothing can escape a black hole...
And nothing can enter a white hole.
That's the idea. They only emit light and matter. They repel anything trying to enter. Igor Novikov coined the term white hole back in '64.
So it's like a time-reversed black hole. Instead of an event horizon of no return, it's an event horizon of no admission.
You could put it that way, yes. Stuff inside can get out, but nothing outside can get in. It spits things out.
Okay, so maybe that's the exit. A wormhole connects a black hole entrance to a white hole exit.
That's the neat theoretical picture. A black hole swallows you, the wormhole tunnels you, and a white hole spits you out somewhere else.
Sounds convenient. Almost too convenient. What's the catch?
Well, the biggest catch is, how do white holes form? We understand star collapse for black holes. What's the reverse?
Good point. Do we have any ideas?
Pure speculation, mostly. Some wonder if the Big Bang itself was like a giant white hole eruption.
The start of everything.
And there are ideas linked to black hole death. Stephen Hawking's work on black hole evaporation.
Hawking radiation, right? Black hole slowly shrinking.
Yes. And quantum physics has this idea, the no-hiding theorem, basically saying information can't be truly destroyed.
Okay.
So maybe as a black hole evaporates and dies, all the stuff and information it swallowed has to go somewhere.
And it comes out through a white hole. Like cosmic recycling?
It's a very speculative but fascinating possibility. Connects the beginning and end of black holes.
But didn't you say there was a problem with physics laws? Thermodynamics?
Ah, yes. The second law of thermodynamics, entropy, disorder. It always increases in a closed system overall.
Right. Things tend towards messiness.
Black holes fit that they swallow ordered stuff, increase overall entropy, but white holes, they'd be spewing stuff out, seemingly decreasing local entropy, creating order from, well, wherever it comes from.
Which sounds like it violates the second law.
It appears to, yeah. And that makes many physicists very skeptical that white holes can actually exist in our universe. It's a major theoretical hurdle.
So any evidence at all? Have we ever seen anything that looks like a white hole?
There was one intriguing event back in 2006. A gamma-ray burst detected by the Swift Observatory, GRB 060614.
A gamma-ray burst. Aren't those usually from collapsing stars, supernovae?
Usually, yes. But this one was weird. It was incredibly powerful, but there was no sign of a supernova, no collapsing star associated with it.
So what caused it?
Nobody knows for sure, but one very tentative, out-there hypothesis was, maybe just maybe. It was a white hole spontaneously erupting, releasing a huge burst of energy.
A one-off observation.
Pretty much nothing quite like it has been confirmed since. So GRB 060614 remains a bit of a mystery, and white holes are still firmly theoretical, just like black holes were for a long time.
Okay, so gravitational wormholes connecting black and white holes.
Huh.
Highly theoretical, maybe impossible. But I read something about scientists making a wormhole in a lab recently.
Ah, yes, the 2015 experiment. That's important, but it needs clarification. It wasn't a gravitational wormhole for travel.
No. What was it then?
It was a magnetic wormhole. They used special materials to manipulate a magnetic field.
Magnetic. How does that work?
Okay, picture a magnet's field lines going from North Pole to South Pole, right?
Huh?
They build a device using metamaterials, including superconductors cooled way down with liquid nitrogen.
Okay.
And they managed to make the magnetic field go in one end, disappear from the space between, and then reappear out the other end.
Like the field took a shortcut through an invisible tunnel.
Exactly. The magnetic field behaved as if it had traversed a wormhole, connecting the 2 points magnetically while being undetectable in the space linking them.
So, it's a wormhole, but only for magnetism, not for me or my spaceship.
Precisely. It's a fascinating demonstration of manipulating fields, and it's analogous to how space-time might bend in a gravitational wormhole, but it's not the same thing. Doesn't help us get to Andromeda any faster.
Got it. Still cool, but not quite interstellar.
Mm.
So gravitational wormholes have huge theoretical question marks. Are there other faster-than-light ideas from Einstein's work?
There are other theoretical possibilities, yes. Another famous one is the Alcubierre drive.
Alcubierre, Miguel Alcubierre, 1994.
That's the one. Again, it's a theoretical solution to Einstein's field equations, but instead of a tunnel, it's about warping space around a ship.
Ow.
The idea is to contract space-time in front of the spacecraft and expand space-time behind it.
Creating like a wave. A bubble.
Kind of, yeah. A warp bubble. The ship itself wouldn't technically be moving faster than light within its local bubble of space-time.
But the bubble itself, carried by the expanding and contracting space, could travel faster than light relative to everything outside it.
That's the theory, like riding a wave in the fabric of space-time itself.
Sounds very Star Trek.
Mm-hmm.
But I bet there are catches there, too.
Oh, absolutely. Huge catches. The energy requirements are calculated to be astronomical, possibly requiring the mass energy of entire planets or more.
Yikes.
And it seems to require something called exotic matter stuff with negative mass or negative energy density.
Negative mass. Does that even exist?
We've never observed it.
Yeah.
It might be theoretically possible in some quantum contexts, but we have no idea how to create or handle it, even if it does exist. So the Alcubierre drive is also firmly in the realm of fascinating but highly speculative theory.
Right.
Yeah.
So, okay, let's try and wrap this up. This has been a lot to take in.
It's definitely mind-bending stuff.
So wormholes. They come out of Einstein's math, a theoretical possibility for a shortcut through space, maybe even time.
But fraught with challenges. How they form, how they stay open, what's on the other side.
And white holes, the theoretical opposite of black holes, might be linked, but they have their own issues, like potentially violating thermodynamics.
And while we've made magnetic analogs in labs, the real gravitational deal remains elusive.
Still, it's amazing that the same equations that describe gravity and black holes also contain these wilder possibilities.
It is. And even if wormholes or warp drives prove impossible for travel, exploring these ideas pushes our understanding of physics, of space, and time itself. Scientists are always looking at the edges of what Einstein's theories might allow.
Absolutely. It really leaves you thinking, doesn't it? If Einstein's equations open the door to things like black holes, which seemed impossible until we found them, and suggest things like wormholes, what else might be hidden in the math?
What other aspects of reality are described by those equations that we haven't even conceived of yet?
Exactly. What other fundamental shortcuts might exist, not just in travel, but in our very understanding of how the universe works? Makes you wonder what's still waiting out there in the fabric of reality.